heat flux is directly proportional to the temperature difference, which is Ts minus T infinity. So heat flux is directly proportional to temperature difference here. Now we can write this heat flux as heat transferred per unit area, which is directly proportional to Ts minus T infinity. Now in order to remove this proportionality, we will use a constant called H multiplied by A into Ts minus T infinity. Now this H is called convective heat transfer coefficient. Convective heat transfer coefficient. And its unit is watt per meter square Kelvin or watt per meter square degree centigrade. Now, coming to this convective heat transfer coefficient, it is not a material property like thermal conductivity. So, convective heat transfer coefficient is not a material property and it depends upon three different parameters like the geometric parameters, fluid parameters and flow parameters. Geometric parameters, fluid parameters and flow parameters. Geometric parameters means, as this is a plate, we consider length of the plate. When we take a pipe in which fluid is flowing and heat transfer is taking place by convection, then we need to take the pipe diameter as well as length. Like that, if we take a duct, rectangular duct, we need to take different dimensions. So based on the dimensions or geometry of the object through which the fluid is flowing, this convective heat transfer coefficient varies. So that is the geometric parameters which affect the convective heat transfer coefficient. Coming to this fluid parameters. So fluid parameters means fluid density, fluid viscosity, all this comes into picture while taking this convective heat transfer coefficient. So this convective heat transfer coefficient depends on the geometric parameters like the dimensions. Second thing, it depends on the fluid parameters like the fluid density, its viscosity, all these things. Then coming to the flow parameters, the velocity with which the fluid is flowing over the surface, because more the velocity, more will be the heat carrying capacity. So velocity as well as acceleration, these two come under the flow parameters. So this convective heat transfer coefficient is not a material property, it depends upon all the three parameters like geometric, fluid and flow parameters. You need to remember that. Now we can write this particular equation as Ts minus T infinity by 1 by HA. This is equal to Q. This equation is analogous to the Ohm's law, I is equal to dV by R. So current is because of potential difference, whereas heat transfer is because of temperature difference. So here for the flow of electrons, the resistance offered is electrical resistance, whereas for the flow of heat, the resistance that is offered, we call it as the thermal resistance. So the thermal resistance for convection will be 1 by HA. So 1 by HA is the thermal resistance for convection, and here also the unit for thermal resistance will be Kelvin per watt. You need to remember this. Now here we can draw the electrical analogy diagram like this. So as the surface is at higher temperature, heat flows from the surface to the fluid, and the resistance offered is the thermal resistance due to convection, and it is given by 1 by HA. Thermal resistance due to convection is given by 1 by HA. Now suppose if the fluid temperature is more than the surface temperature, then what will happen is the convection takes place from the fluid to the surface. So therefore this same equation can be written as HA into T infinity minus Ts when the fluid temperature is more than the surface temperature. Okay, so this is the Newton's law of cooling, what we come across. Now coming to radiation. So the basic law for radiation, what we come across is Stephen-Boltzmann law. So according to this Stephen-Boltzmann law, it states that the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. So here the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. Now, in order to remove this proportionality, we need to go for a constant which is called Stephen-Boltzmann constant. So, sigma, we call it as Stephen-Boltzmann constant. The unit of this Stephen-Boltzmann constant or the is 5.67 into 10 raised to the power minus 8 watt per meter square Kelvin power 4. So this is Stephen-Boltzmann constant, and whatever may be the material or anything, this Stephen-Boltzmann constant always it will be 5.67 into 10 raised to the power minus 8 watt per meter square Kelvin power 4. See, the unit of emissive power will be watt per meter square, and T, as we are talking about absolute temperature, temperature should be always considered in terms of kelvins. So temperature should be always considered in terms of kelvins while we are talking about radiation. In case of conduction and convection, you take in degree centigrade also, there will be no difference. But whenever you are solving problems related to this radiation, you need to consider always the temperature in terms of Kelvin, otherwise you are going to get the wrong results. Right? Now, see, when we are talking about this Stephen-Boltzmann law, so here we have talked only about a black body. So a black body, let us consider this as a perfect black body. In nature, we don't have perfect black bodies. Ice can be assumed almost like a black body. So this perfect black body, its emissive power will be fourth power of its absolute temperature. So the temperature of the body, its fourth power will give us the emissive power. Now, we know that without temperature difference, there will be no heat transfer. Now, when it comes to radiation, so radiation happens in between two bodies when they are kept in vacuum or when they are in the environment. Radiation phenomena can happen in both the case. Now let me consider the temperature of this body as T1 and temperature of this body as T2. So let me assume that these two bodies are kept in vacuum, and as T1 is greater than T2 here, considering. So as these two bodies are kept in vacuum, then the only phenomena by which heat transfer can happen is by radiation. Because of a temperature difference, here heat transfer takes place. Now, the heat transferred by radiation from this body to this body, let us consider it as Q1 to 2. So Q1 to 2 will be equal to sigma into area of the first body from which heat transfer is taking place multiplied by capital F1 to 2. This capital F1 to 2 we call it as shape factor. We call it as shape factor or view factor or geometric factor multiplied by small f1 to 2. This small f1 to 2 we call it as interchange factor. Interchange factor, or we can call this as equivalent emissivity. Equivalent emissivity. Multiplied by capital T1 power 4 minus T2 power 4. So this will give us the formula for heat transfer by radiation. So in the entire radiation concept, we will use only this formula for radiation heat transfer, but the things that vary are the shape factor and the interchange factor. This shape factor is completely dependent on the geometry of the object. It completely depends on the geometry of the object, whereas this interchange factor or equivalent emissivity depends on the emissivities of these objects and how the objects were placed. Okay, so these two play a very important role in determining the heat transfer from one surface to another surface. Okay, so this formula we should remember while calculating heat transfer in case of radiation. Now this same formula we can write in this fashion: Q1 to 2 is equal to T1 minus T2 by 1 by sigma A1 capital F1 to 2 small f1 to 2 into T1 plus T2 multiplied by T1 square plus T2 square. So T1 minus T2 by this whole thing we can write. See here, this T1 power 4 minus T2 power 4 I have just split it into T1 square minus T2 square into T1 square plus T2 square. So this will be T1 minus T2 into T1 plus T2 multiplied by T1 square plus T2 square. So this T1 power 4 minus T2 power 4 we have split it like this, and if I take this total thing to the denominator, it comes like this. Now this particular condition is analogous to the Ohm's law, I is equal to dV by R. So current is because of potential difference, whereas heat transfer is because of temperature difference. Here the resistance is the electrical resistance for the flow of electrons, whereas here the resistance is this total term. So this total term will be the thermal resistance due to radiation. So this will be RTH radiation. So the thermal resistance due to radiation. And remember that area will be in terms of meter square, as these two are factors, they doesn't have any units. So therefore here also when we talk about thermal resistance due to radiation, the unit will be Kelvin per watt here. The unit will be Kelvin per watt. Okay, so sigma, the unit of sigma is watt per meter square Kelvin power 4 multiplied by area. For area the unit is meter square multiplied by, for the factors we don't have any units, this T1 plus T2 will be in terms of Kelvin and this one will be in terms of Kelvin square. So therefore Kelvin cube you will have, these two gets cancelled, Kelvin cube and this one will get cancelled. So this will, the denominator term will be in terms of 1 by all these things. So 1 by watt per Kelvin. So this can be written as Kelvin per watt. So I have just taken the unit conversion for this denominator term. So that will be like this. So this total term will give us the thermal resistance due to radiation and its unit will be Kelvin per watt. We need to remember this. So as far as radiation concept is concerned, this formula plays a very important role. Now, let us go for the next thing, thermal conductivity. So, thermal conductivity K. So, this thermal conductivity is a material property. So, it is a material property. So this thermal conductivity varies with respect to temperature, and it is given by K equal to K naught into 1 plus beta T. So K is equal to K naught into 1 plus beta T, where K naught is the thermal conductivity at 0 degrees centigrade. So that is the thermal conductivity at 0 degrees centigrade, and T is the temperature, and beta value, it depends upon the material what we have used. Okay. So it depends upon the material that we have used. Now, coming to this thermal conductivity of solids will be greater than liquids and greater than gases. Again, solids we can classify into metals, non-metals. Thermal conductivity of metals will be greater than the thermal conductivity of non-metals. Again, metals can be classified into ferrous and non-ferrous materials. So here, the thermal conductivity of non-ferrous materials will be greater than that of the thermal conductivity of ferrous materials. You have to remember that. The thermal conductivity of crystalline solids will be very high. So, crystalline solids, when we talk about crystalline solids are diamond, graphite. So, diamond and graphite, they possess excellent thermal conductivity. Now, thermal conductivity of non-ferrous materials will be greater than ferrous materials. Non-ferrous materials like copper, silver, these will have very high thermal conductivities as they are considered as the noble materials which are non-corrosive. So therefore, the thermal conductivity of non-ferrous materials will be very high when compared to that of ferrous materials like iron, steel. Now, when we add impurities like magnesium or some other material to iron or steel, what will happen is generally their mechanical properties will improve. But as far as thermal conductivity is concerned, this is a property that is related to thermal analysis. So therefore, the thermal properties of the materials will decrease when we are adding impurities to the materials. That means the thermal conductivity of base materials will be greater than that of their alloys. So thermal conductivity of base materials will be greater than that of their alloys. Adding impurities improve the mechanical properties of the materials but not the thermal properties. That's why the thermal conductivity of copper will be more than that of bronze or brass. Okay, because they are base materials, adding impurities will not improve the thermal properties of the material. Now, when it comes to solids, the thermal conductivity increases with increase in temperature. So thermal conductivity when it comes to solids, it is decreases with increase in temperature, decreases with increase in temperature. Aluminium and uranium are exceptions. So thermal conductivity of aluminum and uranium increase with increase in temperature, whereas the thermal conductivity of all other solids decrease with increase in temperature. So in the GATE examination, the questions will be asked either from this or from the thermal conductivity considerations here. Now, coming to the liquids and gases. So coming to the liquids, thermal conductivity decreases with increase in temperature. Water being an exception. Water being an exception. Coming to the gases, thermal conductivity of gases increases with increase in temperature. So thermal conductivity of gases increase with increase in temperature. So this concept was asked in GATE 2014 for 1 mark. So thermal conductivity of gases increase with increase in temperature. Now, coming to the thermal conductivity of porous materials. So thermal conductivity of porous materials depends on the liquid or gas present in the voids. So example of this porous materials are pot, like this pot will be there. So for the pot there will be voids, that means small holes will be there. So the thermal conductivity of that porous materials depends upon the liquid or gas that is present in those voids that are present. So the unit of this thermal conductivity, as already learned, this is watt per meter Kelvin. So watt per meter Kelvin. Now, in brief, the thermal conductivity can be defined like this. So from the Fourier's law of heat conduction, Q is equal to Ka into T1 minus T2 by L. So from this, we can write it as Q by A into L by T1 minus T2. So this is given by thermal conductivity. Now, this can be written as, thermal conductivity definition can be written as, it is defined as the ratio of heat transfer to the area and the temperature difference. So that we can write as the definition of the thermal conductivity. Now remember that thermal conductivity is a material property and it always varies with respect to temperature according to K equal to K naught into beta 1 plus beta T. Okay, let's have a break. After that we'll discuss.